Okay, I'm going to use this example to prove that Green's theorem actually works. Let C be the boundary of a triangle with vertices 0, 0, 1, 2, 0, 2. Find the magnitude of the energy enclosed within the triangle, and you're given that the equation of that circular path is given by the integral around a closed path of 4x squared y plus 2y dy. Okay? 4x squared y dx plus 2y dy is the equation. Okay? So, in other words, that's the form, which I'll explain this later, but that's the form integral around a closed path of m dx plus n dy, like that. Okay. All right. So basically what I'm going to do first is I'm going to plot the triangle. And I'm going to use two different methods. First, I'm going to do the direct method calculation, then I'm going to use Green's theorem. Okay, so let's put our 1 out here, exaggerate it. And let's say 2 is up here. This is 0, 2. And over here would be the point 1, 2. And, of course, the origin is going to be at 0, 0. Okay, so I connect the points to draw my triangle. And what I'm going to do it the long way, first I'm going to integrate along this path, and then I'm going to integrate along this path, and then I'm going to integrate along this path. And when I get done, I will find the energy within that enclosed triangle. Okay, so to start out with, I'm going to be integrating, I'm going to be bounded on the x-axis 1, 0. So I'm coming out here to 1. And then I'm going to make the equation y simple. So I'm going to have y as a function of x. Y is going to be some function of x. And it's going to go up to 2. Okay? So in this integral, first I'm going to go this way along the x-axis, because I'm binding at x there, and then I'm going to integrate, and then I'm going to I'm going to go this way first, and then I'm going to go this way, and then I'm going to go this way. Okay, now the first thing we need to do is express y as a function of x, but how am I going to do that? How am I going to get this dy? Okay, well, the first thing you do is you look at y equals mx plus b formula to find the y-intercept equation of the line. Okay? Well, in this case, b is going to be 0. How do we find the slope? Rise per run. Okay? 2 minus 0 over 1 minus 0. Okay? So m equals 2 minus 0 over 1 minus 0, which equals 2. And we know b is equal to 0 because the intercept is 0. Okay, the y-intercept is 0 right here. Okay, so we can write our equation for the line. Y equals 2x. Simple, right? dy dx equals 2. So that means that dy is going to equal to 2 dx. So now we have everything in terms of x. We can put everything in terms of x, and we know that we're integrating from 0 to 1 along the x-axis. So the first curve, call that C1, or the first line in this case, call this C2, and call this C3. Okay, so C1 is going to give us the integral from 0 to 1 of 4x squared times y. Y is 2x. So I'm going to plug the 2x in there, and I'm going to get 8. I'm going to get an 8x cubed dx. And then I'm going to plug in for y here, 2x. 2x times 2 is 4, and dy equals 2 dx, so that's 8. So I'm going to get a plus 8x dx. Now I have everything in terms of x, and really what this means is it's like a distributive property of the integral. Okay, that's the way I look at it. So anyway, when I integrate this, x to the 4th over 4 is just going to give 2x to the 4th evaluated at 1 and 0. And then plus, when I integrate this, x squared over 2, but I got the 8 here, so 2 goes into 8 4 times, so I'm going to get 4x squared evaluated at 1 and 0. And then when I plug in 1, I'm going to have 2 plus, see, 2 times 1 is 2, because 1 to the 4th power is still going to be 1, so 2 times 1 is 2. 4x squared, well, I'm putting 1 in there, so 4 times 1 is just 4 again, and that's going to be 6. So I'm going to write up here, I'm going to say C1 equals 6. The path along C1 equals 6. Call it path. Path C1 equals 6, okay? Now I'm going to go this way, which means that I will integrate from 1 to 0 going that way. Okay, and what's going to happen? Well, y isn't going to go up and down, so there's not going to be any dy, right? So I look back at my original equation, and dy is going to become 0. So all I'm going to have left is this integral from 1 to 0 of 4x squared, and we said that right here y goes all the way up to 2, so y is just a constant, 2 dy, and that's just going to be 8. You're going to integrate from 0 to, from 1 to 0 of 8x squared with respect to x. And then when you integrate that, you're going to have 8 times x cubed over 3 evaluated at 0 and then 1. And that's going to give you a negative value, because 0 minus 8 times a third is going to be negative 8 thirds. So now I have C2 equals negative 8 thirds. C2 equals negative 8 thirds. Okay? All right. So we have 2 of them. And now I'm going to go down this way. So x is going to be at 0, and y is going to go, in this case, y will go from 2 to 0, correct? So now I'm going to say, so x goes to 0, in other words. So now, looking at my original equation, I'm going to have going from 2 to 0. Yeah, 2 to 0, because I'm going this way. I'm going 2 to 0 of the y part of the equation, which would just be 2y dy. And that one's pretty easy because you got y squared over 2 and then multiplied by 2. It's just going to have y squared evaluated at 0 and 2, which is just going to be negative 4. Okay? So I will have the path along C3 equal to negative 4. So the total path is going to be C1 plus C2 plus C3, which is going to be 6 plus negative 8 over 3 plus negative 4. Do the whole integers first, and I get 2. Okay, so that's going to be 2 minus 8 over 3, which is going to be 6 over 3 minus 8 over 3, which will equal to negative 2/3. Okay, so negative 2/3 will be my answer. Going around, I will get a negative 2/3 for an answer. So I write that down on a clean sheet of paper. I will have the total path I figured out the long way as equal to negative 2/3. Okay, now what's going to happen? Well, Green said that if you take the integral along a path of m dx plus n dy, like that, then you can use the formula double integral over a bounded area of partial n partial x. This turns out to be the curl also, by the way. Minus partial m partial y. Evaluate that double integral in a bounded area, and I should get the same answer. I should get negative 2/3 again. Okay, so now let's try that. Okay, looking at rewriting my original function, which is an integral rewriting my original function, which is the integral along a closed path of 4x squared y dx plus 2y dy. Looking at that is m, and looking at this is n. I'm going to say partial n partial x. Partial n partial x equals 0, because the derivative of y with respect to x is just going to be 0. Partial m partial y, partial m partial y is going to be 4x plus 2. Is that right? 4x squared. 4x squared partial m partial. No, just 4x squared. It's going to be, yeah, 4x squared, man. Exactly. So now, according to Green, I have the boundary. Okay, now let's look at our boundary for that area. Okay, so if I integrate from 0 to 1, and then I go from y equal to 2x to 2, okay, so now I know exactly how to do it. So what I'm going to do is my boundary, my outer boundary is going to be 0 to 1, and my inner boundary, my y simple function in terms of x will be 2x from 2x to 2. See how I got that? If I bind it on x, then I have to write y as a function of x. Always write your variable in terms of a function of the bounded x is variable. That's a rule to remember in calculus, okay? So if I write this as a function of the bounded x is variable, which is x, then I get y equals 2x, and y is going to go from 2x all the way up to 2. So now I know my boundaries right there. And I got this minus 4x squared dy dx. And then, okay, now what answer am I looking for again? Negative 2/3, right? Let's see if this evaluates to negative 2/3. Well, if I integrate with respect to y, I get negative 4x squared y evaluated at 2 and 2x. Okay, I'm going to go ahead and evaluate that. So I get negative 4. I'm evaluating y. So 4x squared y. Okay, so I still have the x squared. And then I have y. Minus this negative, which is to be a plus. This 4x squared times 2x. So I'm going to get this function that looks like negative 8x squared plus 8y cubed. And then I still have to integrate that with respect to, sorry, that's not y cubed, that's x cubed. Okay. 8x cubed, and I still have to integrate that, bounded from 0 to 1, like that. And, let me see, is that right? No, that's not exact. Yeah, that is right. That is right. So, when I integrate, I get negative 8 over 3, because I plug in 1, x cubed over 3. So negative, and then I plug in 1 here, so I get that. Plus, and that's going to go x to the 4th over 4, which would be 2x. And 2 times 1 is just 2. Okay. So now I'm going to have negative 8 over 3 plus 6 over 3. Which will equal to, what was I thinking? That'll equal negative 2/3. That's what I was looking for. So in other words, I used Green's theorem, which was a lot faster. I used Green's theorem to come to the conclusion that the evaluation of this line integral, which can also be a curved integral, called a curved, it's not called a curved integral, but you know, it can be along a curve as well. So I used two methods, the straightforward method, and when I used the straightforward method, I got a total value of negative 2/3 right here. I said C1 plus C2 plus C3, and I got negative 2/3. Okay, so, and then I took Green's theorem, and I evaluated the same. I used Green's theorem to evaluate this function, and I got the same answer. Total path equals negative 2/3. Total evaluation equals negative 2/3. And then I got total evaluation here equals negative 2/3. And if you wanted to take the magnitude of that 2/3, If you had units or whatever, then you would just have 2/3, or absolute value, not magnitude, absolute value. Yeah. So it'd be the absolute value of a scalar function. So in other words, what I'm saying is that I evaluated this problem using the straightforward method, going from here to here, and then from here to here, and then from here to here. And then I used Green's simplified method, which is just this all the way. That's it in a nutshell. That's just it, And when I calculated everything using Green's method, I got negative 2/3. So negative 2/3 equals negative 2/3. And that proves that Green's theorem is valid.